Hello, this is Mrs. Jones and welcome to my lesson on energy stores and transfers. This is the first lesson in the paper 1 topic 3, which is conservation of energy. And to start off, I want you to think back to the work you did on energy stores and transfers in Year 8. Have a look at this picture cartoon of a fairground and see if you can identify any energy stores or transfers. And see if you can split them into stores and transfers. And then if you can as well, have a think about energy stores or transfers that are useful and some that may not be useful. Okay, so hopefully you've had time to have a think about stores and transfers from the fairground picture, and I've just listed some of the example energy stores that you might have identified. So first of all, anything that's moving stores kinetic energy. So for example, the roller coaster or the chair ride might be something that you thought about in terms of kinetic energy. Anything that is raised above ground within a gravitational field, so if the height of an object is changing, it will change the amount of gravitational potential energy that it stores. So the higher it goes, the more gravitational potential energy it will store. So the roller coaster going up the slope, for example, is a good one for gravitational potential. Chemical store, anything that's food or fuel, I always say, for chemical energy store. Also batteries, but there weren't any examples of batteries that we could see really, but anything that's food or fuel. So for example, the candy floss is a food. It stores quite a lot of chemical energy because of all the sugar. And then of course thermal. Now everything stores some thermal energy because it's to do with how much energy in terms of kinetic energy the particles actually have. But if we're thinking about it from far away, that not looking at it on a particle level, that everything actually does store thermal energy. So anything that's hot, so for example the human body will be storing quite a lot of thermal energy, and anything that's hot compared to its surroundings. But like I said, even something that seems cold to us does store a certain amount of thermal energy. For the transfers, we've got some examples here. So by radiation or by light, sometimes we say. So anything that's giving off any light, so lights from the fairground will be radiating visible radiation. By heating, so energy being transferred by heating, we can talk about heating in terms of particles and by radiation as well. So we'll have a look at that a little bit later. So anything that's giving off infrared radiation is transferring energy by heating. Something that is being subject to a force, so forces will cause energy to be transferred, what we say mechanically, or we say mechanical work. Sound is actually a mechanical wave, so that comes under the energy being transferred mechanically, but we could also argue that sound heats up the surroundings, so we could say that it's heating by particles, but again we can come back to that a little bit later. That one can go in either of the categories. And then anything that's being powered by electricity, we say that energy is being transferred electrically, so supplying the motors of the rides, they might be powered by electricity, and of course the lights as well. So we say that energy is being transferred electrically. If you had to think about the transfers that were useful and transfers that were wasted, there's a few examples here at the bottom of the slide. So something that's useful is what we want the device or the object to actually do, and other energies that are transferred that we don't really need and that we don't really use with the device, we say are wasted. So you can pause the video and just have a look at a few examples here of the useful versus wasted energies within these transfers that are happening in the example. So during this lesson we're going to have a look at lots of examples of energy transfers and stores, just so we can get used to the correct terminology for those. Then we're going to look at interpreting diagrams and also representing energy transfers using diagrams for devices to show what types of energy they store and how they transfer energy into different stores. We are going to talk a little bit about the law for conservation of energy, and we're also going to talk about that a little bit more in the following lesson on efficiency. So it's really important that you can identify energy types and that you can split them into stores and transfers. So for this topic, you really do need to make a list of the different energy stores and the different ways that energy can be transferred, so you can tap into that knowledge at a later date when you are looking at specific examples of devices or objects and being asked to identify a store or transfer for that particular object. So I made a list here of possible energy stores, though a few of them we talked about in the starter activity, and there are a couple here that we haven't really talked about, nuclear being one of them. So as we said, chemical energy store is the energy that's stored in food or fuel, and also batteries as well is the one that doesn't really come into either of these categories. So battery is a chemical energy store. Nuclear we didn't talk about because it wasn't relevant to the starter activity, but nuclear energy is that energy that is stored within atoms. So sometimes it's called atomic energy, and it's stored within the nucleus of an atom. So if you are doing triple science, then you learn a lot more about that when you do nuclear physics in topic 6, which is the radioactivity topic. Anything that's moving that has a mass stores kinetic energy. The equation for kinetic energy we talk about a little bit later in this topic, but the amount of kinetic energy that an object stores depends on the object's mass and also the object's speed, so how fast it's actually moving. Thermal energy, I did say before that everything stores thermal energy because the amount of thermal energy is dictated by how much kinetic energy the particles actually store and how much they are moving or vibrating. So everything stores thermal energy, but some objects store more thermal energy than others. And again, there's something that you revisit much later on in year 11 when you look at particle theory and we look at some equations for thermal energy. So it's a little bit more complicated later on in the course. Anything raised above ground, I talked about this already, stores gravitational potential energy. So we normally refer to it as changing gravitational potential energy if you are changing an object's height. So if you're going up a ladder, for instance, you're going to increase the amount of gravitational potential energy that you store. Gravitational potential energy, we will look at the equation when we look at the kinetic energy equation, and it depends on the object's mass, the object's height, and also the gravitational field strength on the planet. So we'll come back to that in a later lesson. Another one that we didn't talk about was elastic or elastic potential. Sometimes they call it strain energy, and if something is stretched like an elastic band, then it will store elastic potential energy. And then again, something we don't really talk about until year 11 in any great detail, but electromagnetic. So if you are thinking back to maybe even primary school or year 7 when we looked at magnets, then you will know that magnets have the ability to exert a force, and that is due to their store of energy in the electromagnetic sense. And again, we'll come back to that in year 11 when we look at electricity and magnetism. Ways that energy can be transferred, again, we've already talked about all of these, just not in any great detail. So if something is transferring energy due to force, then we would normally refer to that as mechanically or work done or mechanical work. Same with electricity, sometimes we say it's being transferred electrically or by electrical work. So if something is running on electricity, then energy is being transferred electrically. Heating can be split into 2 categories. So by particles would be conduction and convection, which again you learnt about when you were in year 8 when you looked at heat transfer. And then by radiation, so any energy being transferred by radiation, so infrared radiation or maybe other parts of the electromagnetic spectrum such as visible light or X-rays or radio waves would come under this category of heating by radiation. This slide here just gives us a little bit more information about heating by particles and heating by radiation and the difference between them. So for heating by particles, we're thinking really about conduction and convection where particles are involved to transfer energy. So it's just saying here that some objects are hotter than others. Now, all objects store thermal energy and will be radiating and transferring energy to the surroundings, but usually what will happen is that a hotter object will transfer energy to a cooler object, or heat will move from the hotter area to the colder area, and the objects or the environment will start to become closer in temperature, so the difference between them will actually decrease. So if you place an object that's hotter than the surroundings into a hot object into a cold area, it will eventually cool down and become the same temperature as the surroundings. Heating by radiation, as I mentioned before, talking about the electromagnetic spectrum really, which you've probably not done a lot of work on at this point, but visible light is the radiation that we can see. Infrared light is the radiation that we can feel as warmth. Microwave we can't see or feel, and the same with radio waves, but they're all forms of radiation and can transfer energy by a wave. So because it's a wave and it's an electromagnetic radiation, it can travel through space, it can travel through a vacuum. So it's a little bit different than heating by particles, because particles requires actual atoms and material for it to happen, whereas heating by radiation doesn't require any particles or matter. This slide just gives a little bit more information about energy being transferred mechanically and electrically. So in terms of mechanical work, we're looking at forces causing a change in motion or a change in position of an object. So for example, as something falls to the ground, the object's weight is causing it to fall to the ground, and that's the force that's causing it. So we say that energy is being transferred mechanically. Another example is sound waves. They are a mechanical wave and they cause particles to oscillate backwards and forwards, and they can transfer energy from one place to another. Also seismic waves are mentioned here, which are the earthquakes that are caused by earthquakes, and they cause energy to be transferred through the ground material and the earth structure from one place to another. So that's just another example. And anything that is being run on electricity needs a complete circuit to run. So electrons, which are the charged particles, will flow through the wire and through the components and cause energy to be then transferred in other ways as well. So for example, by radiation or by heating, for example. So just a bit of extra information there, some examples for each of those. Okay, so what I'd like you to do now is have a look at these 4 examples. So we've got a kettle, we've got a catapult or slingshot, we've got a concert, and we've got a hot air balloon. See if you can identify the energy stores and transfers involved with these particular objects. So pause the video, have a go, and then come back after and have a look at the information. Okay, so the first one was thinking about the kettle, which is a real classic example for GCSE Physics and for Key Stage 3. Energy is being transferred to the kettle electrically, so we've got bioelectricity here, as it's a device that you plug in, and then energy is transferred to the water by heating. So the electricity that runs through it causes an element in the kettle to heat up, and that then heats up the water. So we say energy is being transferred by heating to the water and to the body of the kettle, because the kettle itself gets hot as well. And then the kettle then transfers energy by heating to the surroundings. So some of the water will evaporate, but also you've got radiation as well. So energy being transferred by heating both ways. Then we can say that the energy then stores the energy as thermal in the actual physical body of the kettle, and also stored as thermal in the water, and of course energy being stored as thermal in the surroundings. In the catapult example, we've got energy being stored in the elastic rubber part as elastic potential energy. So when the person uses their muscles to pull back, so energy transferred mechanically, thinking about the pulling back, but then energy stored as elastic potential energy once the rubber part is stretched. And when that gets released, the energy that's stored as elastic potential energy gets transferred mechanically, because it applies a force to the stone and it applies a force to the catapult. So what will happen is the stone will accelerate due to that force, and it will fly out, and then we've got kinetic energy stored in the moving stone and in the moving bit of rubber band. For the hot air balloon, it starts off with a chemical energy store in the fuel. So we've got a fuel being burnt here. So when the fuel is burnt, it starts off as a chemical store, then it gets ignited and it starts to transfer energy by heating. and by radiation as well, but the useful energy transfer here is by heating, and that then heats up the air that's inside the balloon, and the balloon sort of traps that air that is getting hotter, and the pressure increases, and that actually causes an upthrust force on the balloon, which is what makes it rise up into the air. So energy is transferred by heating and then transferred by mechanically due to this upthrust force from, it's to do with pressure, but again you'll learn more about pressure and gas pressure in year 11 towards the end. And then once the balloon gains height, of course it stores gravitational potential energy, so as its height changes, the amount of gravitational potential energy that it stores will also change, and it will increase as the hot air balloon gets higher. The last example that I asked you to think about was the concert. So we've got quite a few things going on here, but just want to talk about quite a lot of these energy transfers are energy transfers by electricity, because we've got the lights and the sound system and various things that are producing different energy transfers. So first of all, we've got energy being transferred electrically. And just to make a point really, that the electricity is coming from a power station, and the power station is going to be using some sort of fuel to produce this electricity. So the original energy store for energy being transferred by electricity will be some sort of fuel, so it might be coal, oil or gas, it could be nuclear fuel, or some of the energy is being generated using renewable energy resources, so it could be solar powered or whatever. So in terms of energy being transferred electrically, it's coming from somewhere. The energy store is coming from a different place. So energy being transferred electrically to light and sound, and we're getting energy being transferred by radiation or by heating, by light, and also mechanically by sound, which will end up as thermal in the environment, which is what it says here at the bottom about the energy will end up all being stored as thermal energy in the surroundings in the end. So energy coming from people as well, the heat energy that's being transferred, or energy being transferred by heating from the people's bodies, and that's where everything really ends up. It ends up in the surroundings being stored as thermal energy. So there's a little activity here for you to do. So what you can do is have a look at the words in red or terms in red at the bottom, and look at the gaps in the paragraph, read through the paragraph, decide which words go in the gaps, and then you can unpause the video and come back for the answers. Okay, so for number 1 you should have got chemical, for number 2 you should have got gravitational, for number 3 you should have got potential, for number 4 you should have got kinetic, number 5 was thermal, and number 6 was by heating. Hope you did well. Now this is a really important idea in physics. It's something that comes up time and time again. You may have come across this in one of your year 8 lessons. It's the law of conservation of energy. It is coming up now in topic 3, and it comes up in paper 2 as well. The exam board want you to remember this for both paper 1 and paper 2 for GCSE and combined physics. So it's one of those things that you need to write down and you need to learn and of course understand. But it's not that difficult a concept. It is just telling us that we cannot make energy, so energy cannot be created or destroyed. So it can't be made and it can't be destroyed. It's only getting transferred from one store to another store. But quite a lot of energy in transfers gets wasted. It depends what device we're looking at, what object we're looking at. But when energy gets wasted, it goes into the surroundings, and it's really hard to reuse. It's really hard to kind of get hold of. And we say that that energy is being dissipated, so it's just lost and it spreads out into the surroundings. And this is always by heating, so either by particles or by radiation. Even sound is a mechanical transfer, but it does end up as thermal energy stored in the surroundings. So when energy is wasted, it's dissipated into the surroundings and it can't be reused. It just kind of goes into the environment and heats up the surroundings and can't really be used again. So it's important when we look at different objects and devices that we can identify which energy transfers and stores are useful, what we're looking for, and how energy is wasted. And more often than not, it's going to be energy wasted by heating that's transferred to the surroundings because of the force of friction. So again, it's important to not get mixed up between energy types and forces. So friction's a force, but it causes energy to be transferred by heating, and then it's dissipated into the surrounding because of that. Okie dokie, so now we know how to identify different energy stores and transfers, we can start representing them in these energy transfer diagrams. So there's an example here at the top for the kettle, which, like I said, is the classic example. And what we normally do is we normally show energy transfers with an arrow and then energy stores in a box. Next lesson, when we look at efficiency, we'll look at a different type of energy transfer diagram called the Sankey diagram, which again it's another way of representing these energy transfer diagrams, but sometimes they are written out like this. And what we're seeing here is energy being transferred electrically. Like I said before, that is originally coming from a power station and is going to come from a chemical or a nuclear store of fuel or come from a renewable energy resource. But energy being transferred to the kettle electrically, energy being transferred to the water and to the kettle by heating, by particles, and eventually it all gets transferred into the surroundings by heating and ends up as a thermal store in the water and in the body of the kettle and in the surroundings, like we said before, but just setting it out as arrows and boxes. So what I would like you to do is I'd like you to try and draw an energy transfer diagram or energy store and transfer diagram like this one for these three objects. So what you can do is you can pause the video, have a go at writing out an energy store and transfer diagram like this one, and then come back for the information and compare what I've got to what you've got and see if you can get some of these right. Okay, so first one was burning candle. So what we've got here is we've got a chemical store in the wax, because the wax is a fuel. So when the candle's not burning, it's just being stored chemically in the wax that the candle is made of. And then when we light the wick, the fuel will start to burn, and what will happen is energy will then start to be being transferred by heating, by both particles and radiation, because you'll have a bit of conduction, lots of convection and radiation as well. Obviously you've got light and heat there as well that you can detect with your eyes and with your hand if you get close enough. And that then gets converted into a thermal store in the surroundings. So all of the energy that was stored in the wax ends up as thermal store in the surroundings. There might be a little bit of sound as well, which I haven't included here because I've tried to keep it simple, but another way that energy is going to be wasted is going to be transferred by sound. But again, it's all going to end up as thermal energy store in the surroundings. For dropping the ball, if we think about holding the ball above ground to start with, it's storing gravitational potential energy. So the higher you hold it, the more gravitational potential energy it will store. And then when you release the ball's weight causes the ball to fall. It's gravity that causes it, but the weight is caused by gravity acting on the mass. So the energy is transferred mechanically because it's due to a force, and it will fall to the ground and it will increase in speed. It will gain velocity as it falls. So as it falls and as it speeds up, it starts to store more and more kinetic energy. So the faster that it's moving, the greater the kinetic energy store is going to be. Now, as it falls through the air, there'll be air resistance, friction happening, which will cause some of the energy that it's stored as gravitational potential to convert straight to a thermal store in the surroundings, because it will end up being transferred by heating. Again, not included that here because it's a wasted energy, but if you identified that, that's brilliant. If you identified that as well as what we've got here, because that was the challenge really, to see if you could also identify the wasted energy transfers and stores that were relevant to these examples. So if you talked about air resistance causing energy to be transferred to a thermal store in the surroundings by heating, then that's absolutely brilliant if you've managed to come up with that as well. And then the last one was firing an arrow. So you've got the person is stretching the bow back ready to fire the arrow, and that means that energy will be stored as elastic potential in the stretched bow. So it's a little bit like the catapult example from further from the start of the lesson. And then once that arrow is released, the force that is caused on the arrow will then cause the arrow to fly out, and then the bow will also move, and there'll be movement going on. So energy is transferred mechanically because it's to do with the force that is being exerted onto the arrow and onto the elastic. That will then get stored as kinetic in the moving bow or the moving arrow. So whenever an object's moving, you've got energy stored as kinetic. And again, it's the same thing. If you thought about the fact that there's going to be air resistance, there might be a little bit of sound, which will all end up as thermal in the surroundings. So energy will be transferred by heating, will be wasted. Then that's excellent because you've thought of that extra bit of information and sort of decided that, yeah, we've got a useful kinetic store because the arrow's moving, but we've also got wasted thermal energy going into the environment. And lastly, there's a little optional activity here for you, which is to write a short story to show different energy stores and transfers, and you can highlight or label the stores and transfers maybe in different colours or in different ways. You can be creative. Okay, that brings me to the end of the lesson on energy stores and transfers. Thanks for watching. Maybe you could have a think about how this little GIF on the final slide relates to what you've learned this lesson.